Welcome to the Basic Warewash Training Course, AutoClaw Services e-learning online classes. Today's module, we're going to cover the basics of chemistry and the principles of cleaning. Before we get started into the principles of cleaning and the basic chemistry of our business, first we have to have a better understanding of the most widely used and the best cleaning agent in the world. Whether we use liquid or powdered cleaning products, it is water in which we must dissolve these products to get good cleaning and sanitizing results. Let's start by saying this. The purer the water, the better it will dissolve the products that we use. By pure, we mean having less mineral content. Water is the most used solvent of all cleaning applications. We must understand how to treat it and prepare it to work for us in the cleaning cycle. In this module, we're going to cover some of the basics of what water hardness is and how to test it. We're going to cover iron content and we're going to talk about the water pH. Water quality is often the culprit when it comes to problems encountered by dishwashing and laundry operations. Water hardness is defined as the combined amount of dissolved calcium and magnesium present in the water in either grains per gallon or in parts per million. Soap reacts with calcium to form a soap scum. When using hard water, more detergent is needed to get things clean. Whether you are cleaning your hands, hair, laundry, or dishes. Some of the effects of water hardness. Scale buildup in the dish machines, which can cause spotting and filming on glasses and dishes. The minerals will react with soap and some detergents to form a soap scum, resulting in higher detergent consumption and less effective cleansing. Greasy food soils react with caustic and strong alkalis, which forms a natural soap. This soap then reacts with the minerals, forming an insoluble curd that will deposit on your dishes and glasses. Water hardness minerals themselves can spot and eventually etch silverware, glasses, and dishes. Measuring water hardness is very important when you are trying to obtain good cleaning results for your customers. This chart shows the breakdown in grains per gallon of where water hardness falls. Soft water is considered from 0 to 3.5 grains. Moderately hard water is 3.5 to 7 grains. Hard water is 7 to 10.5 grains. And very hard water is anything over 10.5 grains. There are two methods available to overcome the negative effects of water hardness. The use of a water softening system. If your customer has hard water, recommend the use of a water softening company or a specialist. Secondly, the use of phosphates or other sequestering agents. These agents react with the hardness minerals, making them inactive. AutoClaw products include sequestering agents to overcome the negative effects of hard water. pH measures the acidity or alkalinity of the water. In areas where pH exceeds 8.3, water is considered high in alkalinity. At these levels, streaking may occur in glasses washed in a commercial dish machine. Less streaking occurs in soft water than in hard water. The more alkaline the water, the more streaking occurs. The higher the dissolved solids or mineral content in the water, the more streaking occurs. The hotter the final rinse water, the more likely that streaking and spotting will occur due to flash drying. One way to solve the problem due to alkaline water is to use an acidic rinse agent. All of our rinse additives that has the plus behind the name, Rinse Aid Plus, Dry-Mate Plus, those are all considered to be acidic rinse additives. High iron content in water leads to staining problems. It can leave stains that can turn yellow, brown, or a red rust color. Staining may occur, especially with coffee or tea, in water with an iron content level above 0.2 parts per million. The use of an iron removal device is usually pretty costly. However, heavy-duty rinse agents and detergents can also be effective against iron staining. Located with your tools in your service vehicles, you should have a basic wear-wash test kit. Inside of that kit, you'll have the ability to test for water hardness. Water hardness tests should be conducted on every customer that you have on your route, whether it be warewashing or laundry. As we seen earlier, water hardness has a great effect on our results. This is what an example instruction card would look like inside of your test kit. Let's take a walk through this to see how the operation works out. First, we obtain a sample of water to be tested. This sample of water should come within the kitchen or the laundry, either out of a sink or a faucet, to be tested. Next, we rinse out a 25 milliliter bottle 2 to 3 times with the water to be tested. Carefully fill that 25 milliliter bottle with water to the black mark of 10 milliliters. Add 3 drops of hardness buffer solution to the bottle and make sure that you mix well. When using reagents for running tests, reagents should be used that the bottle should be held straight up and down. The drop size that comes out is very important. The hole in the size of the dropper tops is designed for each reagent that you use. If you hold the bottles to the side or angle them, you won't get the proper drop size. Once we add the 3 drops of hardness buffer solution and we mix that well, we add 1 spoonful of hardness indicator. Mix it well and completely dissolve the powder. If the solution turns blue, it indicates that you have soft water. If you have a red, a pink, or any indication of this color, you have a presence of water hardness. Next, by holding the dropper bottle of hardness reagent EDTA straight up and down, add in 1 drop at a time. Count the number of drops that you added to change the red color to a total blue. Make sure that you mix each drop in after each drop. If you drop more than 1 drop at a time, you will get a false reading. Remember, 1 drop at a time and mix well. Count the number of drops. Each drop of water hardness testing solution equals to 10 parts per million of calcium carbonate hardness. In this example right here, if your test should run on both hot and cold water sources, to determine the grains per gallon of hardness, divide your parts per million of hardness by 17.1. So if we dropped 17 drops of hardness reagent EDTA, that would be equal to 170 parts per million. You would take that number, divide it by 17.1, and you would get your grains of hardness per gallon of water. Make sure that you can conduct this on each one of your customers and make note of it on your route cards. Next, we're going to cover the principles of cleaning. As represented in the chart, the 5 principles are equally important to obtain clean dishware. To maintain quality results, A decrease in one principle must be offset by increases of other principles. What this is saying is that this is a complete wash pie. It needs to stay in a complete circle. If we decrease one of the pieces of pie, and again, in this one, it shows that our temperature has fallen out to 100 degrees. Each of the other pieces of pie must be increased to overcome the deficiency of the temperature. So if we're looking at dish machines in this scenario right here, and our temperature is down to 100 degrees, we have to be able to increase one or more of the other principles to overcome this deficiency. Can we increase time on dish machines? Can we increase mechanical action? Where does the mechanical action come from? Can we increase chemicals? These are all things that we need to take a look at. Can they increase or produce better results by better procedures? Let's break each one of these principles down and take a look at it a little bit closer. Let's start out with the principle of time. Sufficient time must be allowed to obtain adequate cleaning results as well as rinsing and sanitizing. Water and time will dissolve almost any soil, but time is money. Total cleaning costs are minimized when labor costs are reduced through an optimum balance of contact time, mechanical action, temperature, and chemical action. So again, take a look at your dish machines. How long does the cycles run? How much wash time? How much rinse time? How much dwell? Temperature, another principle of cleaning. Water must be maintained at significantly high temperatures to obtain a high percentage of soil removal. Again, we recommend a minimum temperatures of 140 to 155 degrees for adequate results. Cleaning efficiency can drop substantially with decreased water temperature. Based on the health department regulations, a minimum of 120 degrees Fahrenheit is required. Hot water may be used for sanitizing rather than chemicals. In this case, final rinse temperatures must be above 180 degrees to kill harmful organisms. Remember this, the speed of a chemical reaction is doubled for each 18 degrees rise in temperature. Let's repeat that. The speed of a chemical reaction is doubled for each 18 degrees rise in temperature. That's significant when we're running from 120 degrees to 140. Cleaning mechanisms. Again, not one of the principles, but one of the things that we must understand, how are we actually removing soil from the hard surfaces that we're working with? Sufficient chemical concentrations must be maintained for proper cleaning, rinsing, and sanitizing. Chemical action during the cleaning process includes wetting, neutralizing, saponifying, emulsifying, chelating, defocculating, and anti-redeposition. Wetting. By itself, water has difficulty penetrating the greasy soils. Warewash products contain ingredients such as surfactants and wetting agents that reduce the surface tension of the water, allowing it to get between the hard surface and soil to loosen the soil. Once loosened, the soil can be removed. Neutralization. A chemical reaction when an acid or an alkaline come in contact. Most soils are acidic in nature. To be removed, must be neutralized. Alkalis or built detergents contain alkaline materials that allow neutralization to occur. The lower it is on the pH scale, the harder it is to clean. Dissolving. A solid being absorbed by a liquid when mixed. Some soils are water soluble and can be removed with water alone. Other soils, such as protein, are more difficult to remove but will dissolve or go into solution in alkaline solutions. Saponification. Saponification is a reaction of an alkaline material with fatty acids found in vegetable or animal-based soils to form soap. Petroleum-based greases or oils cannot be saponified. Usually saponification is associated with food fats and soils. Emulsification is the action of a surfactant or solvent that breaks up petroleum-based greases into small particles and keeps them separated and suspended in the wash solution until they are rinsed away. Soils removed by emulsification are usually mineral oils, such as lubricating oils, motor oils, makeup, body lotions, etc. Deflocculation. Solids that are stuck together are dispersed by adding an alkaline material to raise the pH. This process usually breaks down the soils into small particles and introduces electrical charges to all particles, causes them to repel one another and remain in suspension. pH. We talked a little bit about pH earlier and how it affects our cleaning based on pH being high. So let's take a little more deeper look at what pH actually is. This is a term that is used to indicate the degree of alkalinity or acidity in a solution. The pH graph, you will notice that the starting point of the chart is 0 and the chart ends with the number 14. You will also notice that the center of the chart is 7. That represents pure water. Water, for the most part, is neutral. Water means that it's not acidic nor alkaline. As the numbers increase from 7 to 14, the chart shows an increase in alkalinity. Alkalis are typically used to clean organic or acid soils. Acid soils are such as grease, fats, and oils. Generally, machine dishwash compounds are very high in alkalinity. Many laundry products are also high in alkalinity. In the food service area, to clean floors, hoods, ovens, deep fat fryers, pots and pans, or tableware, it would require the use of alkalis. Acids are typically used to clean organics such as lime and mineral deposits or alkalis. Alkaline soils are soils such as limescale or rust deposits. A typical example of the mineral deposit buildup found in a kitchen would be at a steam table, where water is kept hot, and pans of food are kept sitting in the hot water. To remove this mineral deposit buildup, it would require the use of an acid-based product to dissolve or descale this soil. Acids are also used to neutralize alkalis, just as alkalis are used to neutralize acids. An example of this neutralizing process is when you have a case of heartburn or acid indigestion. To get relief, you may reach for an Alka-Seltzer. Alka-Seltzer is slightly alkaline, having a pH of about 8.3. The alkali in the Alka-Seltzer neutralizes the acid in your stomach to give you instant relief. Some other supporting elements. These elements play an important role in assisting in the cleaning function. As products are blended, these other elements are added to help the alkalis or acids achieve the overall cleaning goal. Sequestering agents. Sequestering agents are added to keep the minerals in the water from interfering with the cleaning process. Sequestering agents surround or tie up mineral deposits. In hard water areas, it is necessary to use a product that has a higher content of sequestering agents. Chlorine, or sodium hypochlorite, or bleach, is capable of removing the color from a stain. Chlorine on its own does not clean the stain. Chlorine also is an EPA, Environmental Protection Agency approved sanitizer. At proper parts per million levels of chlorine to water, this solution will kill most bacteria. Surfactants, or surface acting agents. Surfactants are wetting agents. They simply make water wetter. Surfactants, when dissolved in water, gets between the surface and the soil and allows the soil to be removed. Our next principle of cleaning is mechanical action. Physical or mechanical means of removing dirt, soil, or other particles must be present for adequate cleaning. These actions include brushing or scrubbing and the spraying action of the water. So types of mechanical action that we run across in dishwashing is brushing, scrubbing, pressure, agitation, or vacuum. The purpose is to loosen and remove the soils, increases effectiveness of temperature and chemical action. Some cautions to take with mechanical action. Can scratch, break, tear, distort surfaces. Impeded by malfunctioning or improper equipment. It is procedure sensitive. Poor procedures equals poor results. It's also diminished results from lime scale buildup, soil buildup, a low wash pressure. Our last principle of cleaning, and often most overlooked, but has a tremendous impact on the other four principles. It is often the cause of poor results. Procedures can include scraping, pre-wash activities, loading of machines or the racks, stacking and storage of clean dishware. Remember, 50% of your service is watching and listening of what goes on in that kitchen. Pay attention to how your procedures are for your customers and offer suggestions or advice in how to improve those procedures for better results. To learn more about basic chemistry or the principles of cleaning, by talking to your manager, regional manager, or vice president, or contacts here at the home office. Have a great day.